Okay, so it's already 2:10. It's our pleasure to have Kristen today. You all know him, so I will only mention that it's very hard to describe Kristen's research because it's actually very broad. So if you go to ADS and type Kristen Menou, you will find that he worked on supermassive black holes, electromagnetic counterparts of LISA, protoplanetary disk dynamics, atmosphere of exoplanets, habitability, and more recently on machine learning. So he will tell us about machine learning today, how it can be applied to craters, planets, and redshifts. Yes.
Thank you, Cristobal. Much of the work that I'll present today is actually the result of machine learning workshops that I co-organized with some of the postdocs in the room, and some of the students even attended. And so what we did is basically a mix of training ourselves in machine learning over the past 2 years and then actually looking for maybe good topics on which to apply the machine learning as a tool to make some progress on scientific topics. Now, this is a bit of a last-minute talk that Cristobal asked me to give. And so as I prepared my talk and I had sent my abstract, I realized it's quite ambitious to cover 3 different topics and then an intro to machine learning and then an intro to deep learning all in one talk. So as you'll see, it's going to be mostly a high-level overview of all these topics and the techniques. And then so maybe I'll leave out a number of the details to maybe questions after the talk if people are interested. So the 3 topics that I'm going to discuss in terms of astrophysics are the possibility to use machine learning to perform fast evaluation of the dynamical stability of planetary systems. That's work led by Dan, and he's going to give a talk in a few weeks, I think, about this. Then I'll discuss something that I'm sort of finishing now on revisiting the problem of photometric redshift estimation, which is a standard machine learning problem, and trying to ask whether galaxy morphology helps, and if it does it help a lot or does it help little? And then the last topic is going to be about trying to build automated catalogs of lunar craters. That's a paper a work that has just been submitted, actually. And so I'll try to cover these various topics just in a few slides and at the same time give you all the elements of the machine learning part that actually are most relevant to this. So I thought I would start with a sort of a primer on machine learning, supervised machine learning, to make sure we're sort of all on the same page. And to some extent, that's a concept that is not very different from what we used to, I think, a lot in terms of fitting data points. So you could define one of the simplest trainable machine as simply trying to do polynomial least square fitting. So imagine the following situation. I have a sine curve to which, in the domain 0 to 1, in which I add some noise, some Gaussian noise with some amplitude, and then I draw randomly points from that distribution, right? So this is basically my 10 data points here. I'm taking this from a book, by the way, so the figures. So I have 10 data points here, and you know, in real life, I don't know the data distribution, so it's just convenient here. And so something that is often done, I think, in astrophysics is to try to fit the points, to maybe try to simplify, have an idea of how things go, various reasons why you would do that, right? So fitting would go as follows. So you try to fit with a polynomial of order to be specified. And so order 0 polynomial, m is the order of the polynomial. Polynomial here is a constant, so you get best fitting line. Or I should say best fitting in the sense of least square. So do you minimize the square distance between the model, which is a red line, and the data point, that's the blue dots, right? So you try to minimize the mean value of that over the data points. The best fitting line, the best fitting third order polynomial, which is a pretty good job on the sine with noise. And then that's a best fitting 9th order polynomial, which has 10 parameters. There's 10 data points, so it fits perfect. So it's sort of things we know, right? You don't want to go and fit with a model that has actually equal number of parameters or more parameters than the number of points you have.
So I don't agree with this statement.
Sorry?
I don't agree with this statement. That the hierarchy, I think if you do a chi-square test, then you would, in the m equal 9 case, you will get the chi-square is 0. And this is, so what you want to be in a situation where chi is roughly 1. And it's not good if it's much larger or much smaller. So saying that as you add more parameters, the fit becomes better, then I don't, it's not true.
Well, certainly this is a perfect fit by least square measure, right? So you're saying you should not go least square, you should do maybe other measures.
I'm saying if you did a chi-square and you got something that's much smaller than 1, then you have a problem. It's just as bad a problem as getting a chi-square that's much larger than 1. So striving for a better, minimizing chi-square is not a good criterion.
But don't you also divide by like number of degrees of freedom?
Doesn't matter. It's 0. Divide by whatever you want. It's going to remain 0.
Okay, it's sort of irrespective of all this, I'm going to switch to the machine learning sort of view of this problem, which is actually now trying to fit those data points the best you can. But actually, the mindset is slightly different. It's almost the same. It's like, if ever I'm presented with a new data point, in the sense a new value of x, not knowing what the value of my target, so my y-axis is a target here, my x-axis is a feature. I'm starting to use the language of machine learning here. So my input and my output, if you will. If I'm presented with a value x from 0 to 1 randomly chosen, how do I build an algorithm or a machine that actually is most likely to predict reliably what's the value of y? And this one is not going to do well. You can see, right? But so the way you want to do this is actually build your algorithm or your sort of fitting routine, if you will, well, training your machine. And you want to actually reproduce a process of a new data point being shown and actually knowing how well your machine is going to do or your algorithm is going to do on a new unseen data point. So what you have to do is basically remove some data points, let's say 1 or 2, some fraction really of the data points. You put them aside. You actually try to fit as well as you can the existing data that you have for the training and evaluate the performance on data that the algorithm has not seen.
Well, actually, in this case, if you want to estimate the error, error in the extrapolation, then what you would do, you would change the position of each of this point, you would calibrate new variable, and then you would predict it. And then you would add. You would repeat this exercise for each of the point and add this sum of the root sum of the squares.
Are you trying to say cross validation?
No, I'm saying if you suppose that you calibrated the model, you want to know what the error.
What do you mean calibrating the model?
You have a polynomial and you have data points you fit. You calibrate the coefficients of the polynomial. Now you want to check how well the polynomial is going to fit a point that's outside the another point. Then what you would do, you would change each of these points. You would recalibrate the parameters, see how the coefficients change, and then you can calculate with each of these sets of coefficients what the value at the extra point that you want to.
So I'm not sure I follow what you're saying in changing the data points and all this. If that's okay, I'm going to keep going on the yeah. So the workflow for the machine learning on this problem is not trying to fit as best as you can the existing data, but really try to build a predictor for new data with the assumption that the new data will be presented comes out from the same distribution as the data that you already have, for which you already have labels, the y values. And so there is a trick to this, which is that even though so you might choose to go for polynomial fit. You might choose to go for another algorithm and some other ways of actually building the predictor. And even though the machine itself, so the polynomial fit in that case, is not exposed to the validation data, you are, because you evaluate the performance, and therefore you are actually biasing the whole process because you're choosing your algorithm and your parameters based on the validation data. So the good way of doing this is actually to have a third holdout data set that you call the test set that you don't look at for the whole fitting procedure or evaluation. And at the end, you look really how you're doing on a really unseen data point, even unseen by you, if you will. That's sort of the idea. And so I'm trying here to draw a bit of a parallel between like fitting and training a machine. And essentially, it's not far from this like fitting procedure, but you actually have to have this sort of workflow. So that's sort of the workflow of supervised machine learning, you have data points with known targets, and then in the future you think you'll be presented by data points that actually follow the same data distribution, and you want to predict what the outcome should be, not knowing the targets in the future. And so you actually want to be careful about this validation strategy to avoid what's called overfitting in the machine learning literature. It's just making sure that actually your machine is not learned too much on the data you had and is able to generalize quite well on these new data points. And what is being used in the projects I'm showing you now is, of course, not polynomial fitting. It's actually more advanced algorithms. So I won't spend too much time on the algorithms themselves. I just want to mention them here, that dealing with low-dimensional data, scalar data, and I think it's going to be clear what I mean by that a bit later on. We've been using what's called a gradient boosting machine, which is essentially something like a random forest. Many people have heard about random forest, have an idea what that is, but it's further optimized. And it's a rather high performance algorithm. On many data sets, it does well. I can elaborate on that point if you want later on. And then dealing with high dimensional image data, which is of course of interest to us astronomers. We have a lot of images. Basically, it's the use of deep neural network, and specifically a type of them that's called convolutional networks, convnets. And I'll try to explain to you how they work a little bit. So the first topic of interest is planetary dynamics. Just to motivate why you would want to go at this with machine learning, compact planetary systems are unstable. If you put a planet of given masses on orbits that are too close to each other, they'll tend to interact strongly, and then typically you get a planet ejected. You're left over with an excited dynamical systems, meaning high eccentricity, high inclination planets. And this concept is frequently used by astronomers to infer dynamical constraints on the masses, eccentricity, semi-major axis, but I guess more masses and eccentricity and maybe inclinations of planets for which we have only partial constraints on their orbits. The parameter space is quite large in terms of mass, relative inclination, semi-major axis, and eccentricity. And we have excellent n-body solvers to machine precision, essentially. But they are not parallelized, and they are actually they're fast. But then the parameter space is so large that it's difficult to handle that problem in practice for many systems with these n-body solvers. So the question is, can a machine learning solution be offered to this problem? Actually, where you try to learn the planet stability boundary, you try to get a machine to learn the boundary between makes a system stable versus unstable. And the goal would be that then the machine, once trained, might be faster at making a prediction than an n-body solver, I guess.
How can you test for stability with an n-body solver? You can only run it for a finite time, but how can you know that if you had run the same thing for twice as long, then...
Yeah, that's a good question. So in general, the way the system is phrased is exactly for a finite time, is that system stable or not? So that's an example of this.
So you only find them, so you find, so if you find an upper bound for the instability, you go through it.
Let me go through this slide, it should make sense. This is an illustration of this process, maybe with the HR8799 image system. We have beautiful images, even some movie, but we know relatively little about the orbits. We know how much light comes from the planet. But the masses are not really constrained very strongly by this repeated epoch observations. And so what you might do is something like this here. This is actually from the sort of a solar system movie from an n-body solver. But the idea is the following. If you actually try to run the system for an amount of time that is what is your knowledge of the age of the system. And if you bump up too much the mass of the planets, or you bump up too much eccentricities, which again are not very well constrained by the data, then you can establish that the system is likely to go unstable on a time scale shorter than the age of the system. And therefore, that is not something that's allowed by the data. So that's basically sort of the way people use these constraints. And they do that. They've done that on that system, but you also do that on radial velocity data, transit data. It's a very common approach, right? So that's the meaning of this. what region of the parameter space allows for stable systems for a time longer than the known age of the system. This is a problem that has been looked at quite a lot. And so what I'm showing you here is just like I'm sort of finishing on that topic already. You see with how fast I'm covering these topics. Basically, people have established that as you make planets, as you make systems compact in the sense of this mutual Hill radii, which is a measure of the masses of the planets relative to the mass of their star and how close they are, you actually get a time scale of instability that I think scales sort of close to linearly with this parameter here. And so there are all results about this, trying to fit the results of n-body simulations, essentially, for, I think, 3-planet systems. I think this is the work of Alisa here, and Kristen and Dan, looking, I think, at 5-planet systems. It's not, like, really, really important, the details for the point I want to make. The point you see that they have established that actually that stability, the time scale to instability, which is related to, for a fixed time scale to the stability boundary I was talking about, is actually quite a complex boundary, probably related to resonances, mean motion resonances in the system. And so it's a complex boundary, a large parameter space. This is typically a good problem to, and then you're asking for a simple question. Is it stable or unstable on that time scale? Is this something that actually machine learning can do for you? And so we went to, well, actually Dan proposed we do, and then we went to do a couple of years ago, is actually to try to build a machine that would do just that in 3-planet systems, trying to, so that involved actually running, I think it was 5,000 simulations, put 1,500 on the side as a test set, try to have a machine, a gradient boosting algorithm, learn on 3,500, do cross-validation on this, which is like looking at evaluating how well the algorithm is doing, still hiding some data, even within the set that, from which you exclude the test set. This is just this machine learning workflow, basically. And this is optimizing the machine, a lot of runs on multi-CPUs. And then this is sort of the parameter space of that proof of principle study here, which shows you the systems that are known to be stable versus unstable on a time scale of 10 to the 7 orbits of the inner planets. So that's a specific choice of interest here. They're short enough so that we could do this in a manageable amount of time. This is one of this sort of modified version of one of these criterions here in terms of the Hill radii of the planets. And then you can see the true result in the sense of an n-body integration of the system, blue versus red. So you get to be unstable if you're too close to each other, too compact. You get to be stable if you're far away. But there's certainly cases that cross that black lines. There's some measure of how well the algorithm, the machine is doing, and it's doing quite well. And I'll let Dan go into the details of all this, through his talk. I don't want to get too much into the details here. So it's certainly far from perfect. You see that there is a number of incorrectly predicted cases. But I think Dan and certainly we are hoping that it could still, even though it's imprecise, not as precise as an n-body solver, it could be useful still to actually do fast studies of the parameter space and guide some of these decisions about what is a stable system and what is not. And so I encourage you to attend Dan's talk. He's going to go into a lot of details about this, I think.
Just ask, it's 1,000 million, that means 10 to the 9.
So in the paper we said 1,000, but then Dan showed some figures like, no, it's not a billion. So on a specific problem, he showed a case where it was 1 million boost rate. So it depends a little bit on the problem of interest, I think, the boost in, yeah. And that's using, I think, a specific, super optimized machine learning algorithm that's very well parallelized and ultra fast and all this, right? So this is really trying to go at the time, shortening the time so that you can run many such predictions.
So, questions?
Yeah.
Maybe they could be answered in Dan's talk. Is the boundary actually fractal? And if so, would it be a good idea to, instead of do yes versus no, to have a probability over some
Yeah, so I think you can talk to Dan a lot about these things. There's a number of interesting issues that Dan has run into as he was specifically, I would say, I know I talked to Dan about this. So there's a question you're asking, and there's also how to, one of the things that's most useful in machine learning I found from practice is having to define your own data set. You actually have to ask yourself what's the best way for the machine to learn, and actually that way I think you get into ask yourself what's the best way of presenting examples to the machine, what's representative of the parameter space, and all this. And so Dan has thought a lot about this. And so maybe I think you should talk to him, basically. I don't want to get too much into this, and actually I'm not really qualified to answer those questions. I think he would, yeah.
You just asked a similar question, but the enhancement factor, is it infinitely improvable if you have better and better machine learning algorithm, or is it actually finite, meaning you actually have to run the model for a significant amount of time such that there is some feature showing up?
Yeah, so you know a little bit how we did this. One way you can just like feed very few features to the machine, which is the initial conditions, A, E, I of the planets, and then you get a good performance, but you get a significant boost if actually you run a short n-body simulations, and then do the statistics of the orbital variations and selecting features from that, right? Yeah, and that led to a significant boost. Yeah, so I think the way I see it, the limitation is it's a mix of various things, right? But this is a very fast algorithm we're using. I could elaborate on that. It's just like really, really training fast. And so, yeah. So in fact, Dan, do you remember how long it takes to train on 3,500 points? It's like a minute or two. Yeah. It's just like this is things that you can run on a data set of 1 million data points and hundreds of features, and on a good CPU machine, it runs for an hour and it's done. It's just like really, very efficient. Yeah. So then. The issue is how fast you can. This is the time scale here has to do with it's a mix of training and inference. So I think the bottleneck, maybe Dan can correct me, is actually the running the short simulations to build the features of the So maybe that's what you were getting at. Yeah.
There is a bottleneck.
Yeah, I think that's a bottleneck. Yeah. All right. The next two topics are about images. So I need to tell you a little bit about deep learning. And that's just deep learning in a few slides is way over ambitious, but let's see how far I can go. I want to get to tensors, dot products, and then optimization, and then see if it makes sense to you, right? You all, I think probably all heard about deep learning because it's a public word now. But the basic idea in terms of machine learning is that you want to use raw input, high dimensional data. And so, for instance, image or sounds would typically be one of those. And there's different ways. So this is more like a time sequence. This is actually more like, you could think of it as a matrix. It's more like actually a rank 3 tensor, an image if you have color depth, color information. And the typical networks used for that, and I'm going to just discuss basically only that, are called convolutional networks because they operate through convolution operations. And so this type of, I'm going to say convnets are particularly interesting for astronomy. We have so many images, big data sets. It's possible there is more applications of convnets to astronomy that have not been thought of yet. And so the idea behind, so I'm sort of focusing on convnets from now. The idea behind building that machine, the convnet, is going to be to progressively learn features in a space of reduced dimensionality. So this is to be contrasted with what we just discussed, which is in regular machine learning, you actually build the features manually. So for instance, the features that we reduced for that problem of planetary dynamics, you run a short integration, you look at the RMS amplitude, standard deviation of the eccentricity of planet 1, planet 2, etc. So you're building features, and because they contain some information about the stability problem on long time scale, you hope that by feeding that to the machine, it's going to be able to learn more. There is an infinite number of features you can create. So it's a well-known problem that it's all about feature engineering. Having a good machine is all about feature engineering, being smart about finding the right features. And so it can be very exhausting to create all these features and trying the ones that improve and then dropping the ones that don't improve, etc. So that machine learns learns to find features automatically. So it's actually very convenient that way. And then basically does that going through a lower and lower dimensional space. And I showed you graphically what that means here. To the point where actually you get to a low dimensional space that essentially represents what you're interested in predicting. And so you could call that the space of interpretation. In fact, this is called in ML literature the semantic space in the sense of the meaning, what's a meaning. And so an example, if you have images of cats and dogs many types and you want to predict is it a cat or is it a dog, you start with a pixel space, high dimensional, and then you end up in a space which is, I just need two numbers. What's the probability that's a dog? What's the probability that's a cat? And the highest probability, I say, that's a dog or that's a cat. So it's really going from high dimensional to low dimensional. So it's sort of a geometrical way of interpreting what deep learning is in sense of confidence, okay? I like that interpretation personally. It works for me, so hopefully it works for you. All of this is done through tensorial dot products. So you do dot products of tensors going through space of lower dimensionality, and that turns out to be really fast on GPU. So I talked about this fast algorithm. This is just way faster. It's just like unbelievably fast. And then computer scientists have optimized this like hell, so it's actually a wonder of computation. So this is sort of a view of what might be involved in building a ConvNet. So you have an image, 28 by 28. So that's a rank 2 tensor. And then what you do is that you use another tensor, rank 2 tensor, 5 by 5. So this is like basically 25 different values of a number. Those are called filters. And actually, you will optimize the values of those. You don't know what they are a priori. This is what you're trying to optimize. And then once you pass, you slide a convolution on the image like this. So let's say you put your convolutional blocks here, 5 by 5 on the 28 by 20 image. I put it here. I apply the dot product. I get a scalar. So this scalar goes, and it's like my first point here. And then I slide it by a pixel or two. I have choices in how I do it exactly. I get another scalar. And then I slide like this, and I get a new map. That's a feature map. So if I have an image, through the convolution operation, I get a feature map. And then I can actually have a separate convolution filter that can learn different weights in the filter. I get a second map, and a third and a fourth map. Okay, I do that. Then I want to go to the lower dimension. I'm losing some dimension here because of padding. On the side, I can really push my convolution filter. So I go from 28 to 24. There's tricks here. Let's not get into this. I really want to reduce dimensionality, so I go to 2 by, I cut 2 by 2, I take the average, or typically people do max pooling. You max value of the four values here, the 4 nearest values. And then now I have 12 by 4 feature map. I apply another convolutional filter, and then I want to create 12 different feature maps here. That's a choice. You can choose 12 for, this is totally free for you to choose. And then you keep doing that, and ultimately you get into a space that actually has very small dimension in width and height, but elongated dimension in depth. So it's really a three-dimensional geometrical object, if you will, that is operated through convolutions. That's basically what it is. I mean, there's a lot of details, and so you can generalize this by having a third dimension here, rank 3 tensor, which is 3 different colors, typically RGB colors. And then your filters are also 3-dimensional rank 3 tensors, 5 by 5 by 3. And then you keep going like this. So the other thing that computer scientists have been able to come up with is actually a way of efficiently optimizing. So what these feature maps are basically, I have an image, I create features. What creates a feature is my convolutional operator here. And what that operator is exactly is optimized. So what you do is that you pass images, and then you look at whether, let's say, your whole machine here is predicting a cat or a dog accurately. And then actually you propagate back that information in proportion to the error, using essentially the chain rule of, and nothing else. You propagate back that information, and actually, well, I should say, what you're trying to optimize here, which is called the loss or the objective, has to be differentiable. You differentiate it once, so you have a gradient of the loss. That gradient you can propagate back through chain rule, and it tells you how much you have to adjust your weight against the negative of the gradient, which is going to actually improve your prediction on these images. So that's basically a complex machine called backpropagation that is a way of adjusting the values in this 5 by 5 by 3 tensor. And so you go and you show example, and it optimizes the values, and it creates new features, and then that's it. That's basically all there is. And so, how do you use what?
Point layer 2, how does that go from point layer 2, which is more or less 1D sequence to output?
Yeah, so I'm going to show you a different geometry. Yeah, so basically this is no longer used, by the way. This is an old, basically people have dropped these fully connected layers. So, but this might have 12 features, and I might want to predict dog, cat, bird, or whatever if I have 12 of them, so I would have 12 here, but I can also reduce that to 2 here. I connect all these features to actually another 2 neurons, they're called 2 neurons, basically 2 output, which tells me the property of a cat or a dog. And then if this is a rank 1 tensor, if you want to think very elongated, right? The way you connect it in a scalar way by a product plus a product, you basically, a linear combination of all those values is basically what it does, plus a bias, an extra addition. It's just really trivial. So it's basically a linear combination of the features, yeah. Each one is a feature, and then I have 2 probabilities, let's say cat or dog, and then it's a linear combination of those, plus a bias, which is an extra offset. Yeah, that's all there is.
So if all these stages are linear, then basically you reduce the problem. You take any sort of input, you map it onto a very large vector, and then you find another vector that when you multiply both, scalar multiply both, you get a number. And it's one.
Yeah, so the one thing is not shown here is that it's not linear because on top of, it's not shown here, I guess, I realized it. There is what's called activation, which is a sort of a thresholding function that actually makes it nonlinear. And a typical one that you'll hear me mention is called ReLU, rectified linear unit, and it's just like anything negative you put to 0, and the rest you keep. Okay, and that is nonlinear enough that actually this becomes a nonlinear machine.
They were originally trying to use neurons, which have a sigmoid response.
Yeah. And it's simpler with ReLU. Yeah. It works better, it optimizes better. Because there is an issue of propagating all this gradient all the way and have it flow it back in a deep network. It's not, sometimes it breaks, right? So ReLU are good for that in some sense, yeah.
You don't put any information with subsample.
Sorry?
You're not losing any information.
You are, but that's okay. You actually, if you think about it, you do want to a low-dimensional space, which is this cat or dog, right? So you have to go to reduce the dimension, and it works that way. It's just like, I mean, a computer scientist might be outraged by my way of just describing this, right? But I think that's the way I understand it, and it makes some sense. So conceptually, you can think of it as an optimized projection from the image pixel space that's high-dimensional to the low-dimensional semantic space, which is where you interpret things. And then if you feed, let's say you take a 300 by 300 image, which is 10 to 5 features, pixel features, right, plus the colors times 3, to a gradient boosting machine, the one that so if you feed that to a scalar machine, it's going to do poorly. It's just too many features. You just get confused. It takes forever to run. It just doesn't work well, basically. So you have to create features from the images. That's a machine that does it. And so another way of looking, rather than a representation, I think Yantin has gotten the idea here. It's really like this. This is like 28 by 28 times 3. And then I start actually shrinking the width and height and extending in the third dimension until I have something that's basically, so in the case I showed you, I get from 28, 28, 3 tensor to 1, 1, 2. And then one of the neurons gives me the property for the cat and the other for the dog. Yeah?
Is there a way to build in like scale invariance? You see a dog from far away and it's still a small dog, but you had these stencils that were connected to
Yeah. So I think some of those, so that's an topic of importance. I'm not sure I have a good answer on top of my head about this. I think the subsampling might be part of scale invariant. But so this is where it's really interesting. I'm fascinated by deep learning because it's basically geometry, right, that way. And it does rely on a lot of physics, like scale invariance, translation, rotation. They're trying to build machines that are robust to those transformations because the world is. So there is implicitly a lot of physics in this, right? In how you represent the world. I think that's a fascinating topic for any physicist for that reason, right? Anyway, so about the scalar invariance, I should answer you offline, but yeah. So if I were to summarize, because it's going to be useful for later on for a more complex network, this is going from the where space in the sense of where do I have that intensity and that color in the pixel space to a what space, which is it a cat or a dog, okay? And I'm going to show you another more complex network later on that actually does something else. The hype is somewhat justified. It's really amazing. You just show it images, and it builds those. These are the convolutional filters. So in this case, it's from Alexnet. This is from here, from Toronto, in 2012. Jeff Hinton and all this, you have heard about this probably, if you follow a little bit about this. They just did way better than anybody before. The first to put on a GPU and build a machine like this. And so it became so famous that it's called Alexnet. Okay? This is the first name of the grad student, Alex. And so the features that are built, which are the convolutional operators, so I think these are projections of those filters. They have three colors. So I had 5 by 5 by 3. This is 11 by 11 by 3, right? So you project them in the colors so that you get a color image, right? 11 by 11. You get 96 different of those filters. And you might convince yourself, this is obvious to a computer vision expert, I think that some of those will basically do edge detection. If you pass this through an image, it will actually, it's a way of doing gradients. You can see that, right? It's like a 1 and a 0 like this, and it basically does edge detection. But you never told it to learn edge detection. Edge detection is pretty obvious. We do that in our brain and just all the time, right? So that machine has learned to do edge detection. Some of those things people, I think you say, is actually a way of detecting texture. It just learned that by itself. This is just sort of the magic of this. It's just really amazing, right?
You mean you find the correct matrix to be convolutionized?
Well, it finds things that make sense. Yeah, it makes sense that it would try to do edge detection and texture detection and all this. That's what it does without being told. It learns automatically features that are meaningful. And it's actually even, well, I don't know, there is quite amazing results about this, right? So one of those is that it generalizes very well. Maybe just people don't think it's that impressive, but this is trained on 1 million images with 1,000 classes of cars, dogs, and cats, and birds, and trees, and whatever, okay? And then if you take an image in this room, there might be a class that's TV, or there might be, I don't know. But if you take an image from your phone of anything in the natural world, and you feed it to one of these things, it's going to give you a meaningful answer, even though it was not from the data set, right? So it's just really good at dealing with the natural world. Amazingly good, right? So this is just the breakthrough, basically. And then another breakthrough that was built throughout the years that we have reached now is that this does better than an average human. Okay, so I just let's forget about the hype for a moment. It's really impressive. What is interesting from our point of view, you'll see is that it really learns features automatically and can input all the information you have in images, right? So that's really interesting for astronomers. So this is my revisiting the photometric redshift problem. Basically, we are in trouble with LSST. We're going to get a lot of galaxy images, and it's impossible to follow up with taking spectra of all these galaxies. That's just a pretty common situation. It's going to be worse with LSST. People want to do things like constrain the dark energy equation of state and various other things. They want to know the redshift of galaxies. So it's not new. People have said, let me take galaxies for which I have spectra. I know the redshift very well. Look at their colors in, let's say, the SDSS band UGRIZ, and train a machine with many, many examples of colors. Give me the redshift. Learn the redshift from this. And so it's basically a competitive approach to this problem, trying to train a machine to learn photometric redshift. Typically, the solutions use galaxy integrated colors. So you typically feed to the machine something like UGRIZ, actually. And so the question is, can deep learning help here by using the galaxy images directly? We actually do have the images. What we do is that you have a pipeline, and the pipeline goes and says, this is the U color of this is the G color of this. Well, basically, you have UGRIZ images. And then you integrate over the galaxy, you get well, you do the differences, you get the colors, etc. So I guess I should say it's U minus G, G minus R. I'm being a bit loose here in my definition, magnitude and colors. So clearly, there is more information in the images. There is all the information in the images. Can you use it to actually do better photo Z? So people have tried. There's actually a couple papers I know, and then they basically didn't get that impressive results. I'd say nothing that really seemed to improve on the standard solution, as far as I can tell from the papers. And then another thing that has been going on, and there's a recent paper on this, is just people have been a bit confused as to whether morphology helps. So there is a feeling that, is it elliptical or spiral, or other measures like Cerseic index of the profile of light in the galaxy might actually contain some information that would help the prediction. We don't necessarily understand where that is, but can the machine learn that? And so, but the problem with this is that you have to choose the features you want to put and give to the machine, and then you might actually help yourself with one feature, but hurt yourself with another. It's not entirely clear which features to put in, right? So this is where deep learning is interesting, because it will, if there are irrelevant features, the promise is that it will find them automatically. So I decided to give a shot at this. This is my motivation. The major issue I saw in this, and the justification for the specific approach I chose, is that galaxy integrated quantities are features of primary importance, and it's sort of known. It's the best predictor of the redshift, and the morphology might help, but it's probably of secondary importance. We sort of have a astrophysical understanding of this. It's mostly how, the light from the stars, and the galaxy morphology is now the driver of the redshift, of how to estimate the redshift. And so the question is, the question I sort of asked myself is like, can a machine learn to integrate these galaxy quantities, which are basically the magnitudes and the colors? They're basically integrating the light over the galaxy, and at the same time learn the morphology. It's a bit like of a conundrum if you think about it, because on the one hand, if you feed an image, you're asking your algorithm to actually be able to learn how to integrate light to get the magnitude and the colors. But on the other hand, you also wanted to learn to actually decompose the galaxy to get this morphology. So they're a bit like opposite goals, right? And so that actually motivated the approach I chose on this, which is to try to disentangle the features that are like galaxy integrated from the ones that may be morphology. And this is a way you can do it with the beauty of neural network, is that you can just basically, you're totally free to build an architecture the way you want. Several inputs, several outputs, all of that is possible. You see anything that comes up in your imagination. So the way I did this, and there's details about the architecture here, is a custom architecture where on one branch of a network, you feed scalar features, which are the flux of colors and the R-band. I forgot the R-band radius here, the Petrogen radius. It's a standard way of feeding information. And in fact, one of the standard machine learning solution is actually sort of this sort of dense, fully connected network like this, with just a few neurons. It's called ANZ2. I'm hoping to talk to some people who actually know more about Photometric Redshift to discuss this a little bit more. But basically, that's a standard solution. And on the side, I feed actually through a ConvNet branch the images. And then I concatenate the features that are created, and I try to perform the best regression possible on the redshift. And the idea, the motivation behind is the following. When you actually optimize on your, in this case, on your redshift, you try to optimize on your loss. Remember, backpropagation propagates back the gradient and changes the weights, the different weights in the network. It can do that through 2 or 3 or whatever number of branches, and it will do that in proportion to the importance of those features to the final result. So it's able to learn, what I'm arguing is that it's able to learn in the standard way that astronomers are using now, and it can learn the complementary image features, which would typically be morphology, in that other branch. That is what this architecture permits. And so I think I'm gonna actually skip the details on this in the interest of time. The point I'm just gonna make, this is a measure of performance. And you have various points here as you increase the dataset size. Okay, typically you need to feed a lot of data to this convness so that they start doing well. So you might care about only the few points here. There is cross-validated score. You can discard them. What matters is the test score, test performance. So basically you only care about this red dot here, this green dot here, and this the black dot here. The black dot is very bad. That's just a convolutional network. So you feed images and you try to have it do everything. It doesn't do well. The green dot is the one where you only feed the regular way, scalar features, colors, and then you try to do the redshift. So that's sort of a standard method that astronomers use now. And the red dot is my improvement on this, where I actually do the standard, plus have another branch where I try to learn morphology. So my conclusion from this is that, yes, morphology does help. I have a star here. I can explain what there is some caveats here. But morphology, I think, does help photometric redshift. But the gain is actually modest. I'm not convinced it's worth going through all the pain of all this. Because the dark, let's say if you want to do a dark energy equation of state with LSST, my understanding is that you do need to do much better than this. So this might be actually bad news. It's just, I don't see a huge gain that way. Anyway, that's sort of the quick summary of this. And then I'll finish on this. Craters. So craters record the solar system dynamical history via this long-lasting impact. That's just an image of the moon. So typically from the crater size distribution, you can infer a number of things about the impacted population, their size, and the rate at which they have impacted. We have learned about the solar system from this, and we can learn more. You can also date the surfaces from the density of impacts. So it turned out that it seems, and we have not been able to talk to too many experts in that field, but it seems like actually manual labeling is still prevalent. And there is a reason for that. The task here is more complicated. You go and you say, here is a crater, so you have to detect it, and then you have to size it. And I go and I draw a circle and I say, that is a crater of that radius. So we're interested in cataloging in the sense of finding and sizing. So it's actually a complex task. And so people have tried this crater detection algorithms, that's what they call in the literature, and they actually have some success, but they have not been widely adopted. And it seems a reason that they don't do so great at generalizing on new region of the moon on which they didn't train. So this issue of overfitting and generalization that I had mentioned before. And so we actually thought we should give it a shot at this. And then the first thing we had to do is how to frame this problem in terms of deep learning. So one of the approaches we chose is called image segmentation. That's the one that we have adopted and it works. We tried many other things, counting directly the craters on image and various things like this. So it's a lot of work went into this. And then the approach that we finally chose is called image segmentation. And I just want to conceptually explain how that works in comparison to what I showed you before. So the task here is just to take an image and be able to predict a mask. So you learn from pairs of image and masks. You have an input image, and then the mask tells you, this is basically what one of the things people want to do for self-driving cars. They want to be able to say, this is a stop sign, well, this is a sign, this is a pedestrian. So you need to look at an image and say, on the image plane, this is class 1, the pedestrian. This is class 2, it's a bike. This is class 3, another car, whatever. So you actually need to classify on the image plane what you're looking at, okay? That's called image segmentation. And so what the data set available to us would be image. Actually, what they are is digital elevation map. We scratch the actual visual image. The topography maps are much better. There is no issues of how much which side does the sunlight comes in, which complicates things a lot. So it's just like topographic map for the moon. And then we had a catalogs of craters with their location and their size. So we tried first like full disks, but then that hides the crater that's inside. So we actually converge on actually rings as the target. And we trained this big beast to actually learn to predict from an image this sort of pattern here, which is like, basically find craters. And actually from having found them, you can try to fit a circle here and try to get the size from it automatically. And so I just want to explain the sort of the thinking that go behind. So people came up with this architecture. We modified it. It's called a U-net. You see the U shape. It's still working in 3D. And actually, this is pretty much what I showed you before. This is going from the where space, the pixel space, to the what space. You elongate here in this third dimension, right? And then if we put a classifier layer here, you'd just be able to say it's a cat or a dog. That's basically what I showed you before. The problem is that once you're in the what space, you know it's a cat or a dog. That doesn't help you say where is the crater. So you need to go back to the image space. So then you have to go back to the image space. That's what these like sort of deconvolution layers are. So there's a way of like pumping up the size, going back to the original image size. And then so that you like here, that branch, you presumably lose all localized information because that's what you wanted to do. You wanted to go from where to what, cat or dog, not knowing where the cat or dog is, just knowing whether there is a cat or a dog. So then you connect those features here, which do have information of where, to these layers that I've learned about what, and then you go back like this. That's basically the motivation for the structure. And it works great for medical imaging. So people find tumors that way. It really works quite well. And so we decided to try it. And actually it works well for craters. Let me show you the result that some among us postdocs have decided to call this deep moon, a fancy word. This is an example of, I should say, and be careful to train on a third of the moon, validate on a third of the moon, and at the end, just test on the last third of the moon to make sure we didn't like fool ourselves. These neural networks are crazy overfitters, so you have to be careful. And so basically, this is a region of the moon that the machine had never seen before. This is actually the ground truth, human labeled. All the circles here are craters that a human said it's here and it's its size. And then this is what the algorithm predicts. And so it finds a lot of the blue are the recovered from the ground truth. They were in the ground truth. The red are new ones that by looking at it would say they look pretty good actually. This is like the humans doesn't have time to go through millions of craters, right? Because they're too small, there's so many of them that you just cut off at some size. But the machine can go to smaller sizes. And then there's some of the craters in green here that actually were in the ground truth, especially the large one that are not recovered in the prediction. Okay, but the numbers are looking good. 92% of the ground truth craters, the one that were human labeled, are actually recovered by the machine on an area of the moon that it never seen before. So in the sense of generalization here. And actually we feed it digital elevation maps of Mercury, and it seems to do well as well. Just like by eye we look and it's finding craters on Mercury. So it's actually what's called transfer learning. It's another data set, another data distribution. In principle, craters on Mercury may be somewhat different physically than craters on the moon. And yet it's able to transfer the knowledge from the moon to Mercury, which is actually quite an achievement. And so we think this could be potentially a game changer for the field. We are going to release that publicly so that people start using it and see how they feel it should be improved, etc. And so that's it. I basically described to you some of the local expertise that we developed in machine learning and deep learning and applied it to a few problems that we thought were interesting in astrophysics. It's not that obvious to actually find a good use of machine learning in astrophysics, I would say. So the sort of two angles we found is maybe as a way of fast tracking simulation as emulators. You know, the planetary dynamics case is a good example of this. Or if, in the cases where you have actually large data sets that humans are still labeling, it's actually quite useful. You can automate this as well. So it's sort of standard use of deep learning, the second part here. I think there will be extra science coming, I'm hopeful, out of the planetary dynamic stability problem and then the crater problem. I'm not so sure about the photo Z. I think it's a lot of effort for very little gain personally, so I'm a little bored by the problem. But I need to talk to some expert on photometric redshift on this. And then one of the bonuses, I guess, to finish is that several of the people who got involved with this got jobs in the industry because it's like highly sought after skills. And so that's nice to see even undergrads. Undergrads like works and do a 3-month project and then it's just like they get hired by a startup. It's pretty, this happened to 2 of my undergrads. So it's pretty good to see. That's it.
So I'm wondering, what's the size distribution of the missed craters? Do they miss the big ones?
So we have a problem that systematically we see that we're missing the large craters, and we believe it's related to the fact that our convolutional filters are not able to see the larger scale crater. And there's probably a way of fixing that, but we haven't come up with an easy solution yet. And then what we...
Zoomed out image.
Yeah, that's right. So, I mean, this is just like, first sort of results. After months of work, it's working well, and there's ways of improving on it. But it's worth doing it if the community says we want to use that tool, right? Otherwise, we just like publishing in vacuum and not that interesting. So yes, and then what happens here, and that's very exciting to me, is that you find basically you can zoom in rather than zooming out. You can zoom in, and as long as you have the resolution, you can apparently find small craters, and those are the ones that humans cannot label because there is a million of them, and it's more than the lifetime of a PhD student. But then there is a lot of physics on the solar system. The impact of the small bodies is actually very interesting to characterize. And so that's one of my more hopeful extension of this, to look at the small crater distribution. Yeah. Does that answer your question?
Would the size distribution is confused from the ground truth to the new ones? Or you're adding?
So we are incomplete on the small size. So we need to do a better job. We're just showing that we find a lot of them, but there's a number of things we have to look at more carefully. So we know we're finding a lot of them, but we have not really tried to zoom in and really find all of them. And then we need to probably a human expert to look and tell us we have some issues in our team. I haven't done that, but 3 of the authors have looked and say, yeah, that looks like a crater to me. And it's like, no, I'm not sure that is. And they disagree quite a lot. You would think, my thinking before is just like, it's just obvious, right? But no, it's not that obvious. We learn. And then there is disagreement, even at the human labeling stage, which is why machines sometimes can do better than humans to some extent. So you need an expert to look at this and help us sort of. So we don't have the answers for now, but I cannot tell you, but it's definitely an area of expansion, yeah. Yeah.
For the photos used, do you really think that you've reached the plateau?
Yeah, it's a good question. No, I don't think so. Yeah, that's a good question. So, so the lore, there is no, in the machine learning, I find there's very few theorems, and even the theorems are sort of useless. So it's a lot of empirical knowledge. And so there are talks, for instance, by Andrew Ng. He's like a famous Stanford professor. I think he's no longer at Stanford, but anyway, he has plots that he showed that are sort of made up like this, where standard machine learning does very well at small data set size, and the neural networks might not compete that well. So this gradient boosting, for instance, is one of the gradients that does very well. But when you get to actually large data set, neural networks do very, very well, and they keep increasing. There's even some papers about what do you get at a very large data set. One of the reasons you know about this is because there are companies like Google that have the computing power and the staff power to actually do things on. So for instance, they did recently, what I showed you in terms of Alexnet doing well on that competition, it's an ImageNet competition, is 1 million images, 1,000 classes. It takes 2 weeks on multi-GPU to run the model, okay? Google has trained one on 100 million images, 100 times more. I don't know, it's just like all their computers or whatever, okay? And they have shown the sort of improvements you get. So you still get improvements at large data sets. So what I'm trying to say that there is empirical evidence, it's not really well characterized, that you do well as you add more data. And in fact, it seems to be in a parallel manner even. But so I think you can do better. The question is, are you going to collect 100,000 spectra for LSST galaxies? Are you going to collect 1 million spectra? Is it worth it? So it's basically a cost versus trade-off. Yeah.
Well, Boss already has like 1 million spectra.
Yeah, but okay. So this is a really interesting topic. People, you have to be really careful about generalization. And so, well, I guess Boss, okay. I don't think you should be very careful about using an SDSS trained machine and have it predict on LSST, even if you have bands in common. Because this issue of generalization is really critical and it's not trivial. So the telescope is different, the power plant is different, the whatever, and that induces things that can actually fool the machine and bias things. Okay, so you have to be really careful. So I think the way to do it, I want to talk to just experts in this. I think the way to do it is say, let me build a uniform data set for LSST, right? And how many do I need to go? So I think it will get better. I'm not convinced it's worth the effort again. And I'm not the person to answer that question, really, I think, yeah.
Photo Z is not getting better.
Sorry?
Photo Z is not getting better. The green line shows there.
That's the standard method. The red is with the images.
But that's also machine learning. It's not that we couldn't get that.
So
That's also machine learning. But it's not the neural net.
it is. All of that is deep neural net. This is only. So let me just say, I went quickly on this. So I have what's called a multi-layer perceptron. So it's like the regular neural network, right? And then I have a convnet branch, okay? Then what I can do is I can feed zeros here, and on images, I can feed zeros to the images and only those features. That's what I did to see how much they contribute. So the conclusion of this is that you only feed image, it does poorly. If you feed the scalar features, you recover things like what people get in the literature. If you,
Flat, because that's my point.
yeah, that's right. So it looks like with the images, it might be improving better. Yes, maybe. Well, maybe you can improve a little bit. You know, there is fluctuations here. This measures, I mean, the test set, this is on the test set. The test set is relatively small, so you have to have a little bit of grain of salt on exactly where the points are. But yeah, I agree that it looks like it's flattening here, yeah. So, but the point was, if you go to 1 million here, you might be able to do better. Is it worth the effort? I think that's a key question.
I think we'll stop here. We can bring the discussion upstairs. Let's thank Kristen again.